So we've looked at solving quadratic functions. Now we're going to look at quadratic functions and their properties of their graphs. So our objective here, we're going to look at graph of quadratic functions using transformations. So we just looked at transformations of functions and graphing them in our last chapter. We're going to identify the vertex, the axis of symmetry of a quadratic equation. We're going to graph using the vertex, intercepts, and axis of symmetry. And then we're also going to find maximum and minimum values of a quadratic function. A quadratic function is in the form of f of x is equal to a times x squared plus b times x plus c, where we say that a, b, and c are real numbers. And we have to put a stipulation on that a cannot be 0. If a was 0, then we would just have the equation bx plus c is equal to f of x, which is not quadratic anymore, it's linear. The domain of a quadratic function is a set of all real numbers. Notice when we were looking for domains of an equation, we were looking for trouble spots, and those were values which gave us 0 in a denominator, which there's no variable in the denominator there, or negative numbers under an even-powered radical, and there's no radicals there. So the domain for a quadratic is all real numbers. Okay. So let's just kind of go back and recall really quickly about transformations and functions and the effects of the graph. And so our parent function, or the function in our library, was x squared. And so recall that value in front of x squared. So for instance, if we had f of x was equal to a times x squared, and let's say that a was greater than 1, then that vertically stretched our graph of x squared. So we know that our graph of x squared is parabola shape. This point where it changes direction from decreasing to increasing is called the vertex. If that value of a was bigger than 1, that means that the graph was going to grow at a faster rate. And so it was going to be skinnier in here. But notice that if our a value is bigger than 1, if it was between 0 and 1, then it was wider and grew slower. But the point in here is that notice that if our value of a is greater than 0, our parabola is facing upwards. So if our value of a is greater than 0, the parabola faces upwards. And this point in here, the vertex, this is going to be our minimum value, or a minimum point. Recall if our value of a was less than 0, that took our graph and it changed the y values to negative. So that would give us a reflection across the x-axis by our transformations. So if a is less than 0, the parabola is facing downwards, and our vertex is going to be a maximum value. Remember, if we had added something inside, so x plus h, f of x plus h, This was a horizontal shift. So if h was less than 0, we shifted to the right that number of units. If h was greater than 0, we shifted the vertex to the left that number of units. If we added some constant outside of the x squared, so x squared plus k. So if k was greater than 0, it shifted our parabola up. And if k was less than 0, it shifted our parabola down. So notice that if we had an equation written in the form of a all times x plus h quantity squared plus k. So that a value in front of that quantity squared, that's just telling me how wide that parabola is going to be, and is it facing up or is that parabola going to be facing downwards? The plus h, that's telling me if I'm going to shift left or right, depending if it's positive or negative, and that plus k is going to either shift us up or down, depending on if that k is positive or negative. And so technically, this plus h and this plus k, these are going to tell me where my new vertex is from my original function f of x equals x squared. So our vertex is going to be at negative h, as it was the opposite direction than you thought, and comma k. This value here at hk, if I drew a vertical line through hk, our graph is symmetrical across that line. So our axis is symmetry. This is at x equals, well, x value of this point was h. In this case, negative h. So let's actually change this in here. Let's change this to an x minus. You'll normally see it this way. And if it was minus there, opposite sign, so it would be hk. And so our axis of symmetry here would be x equals h. When we're looking at our range, we talked about our domain being all real numbers. Our range is going to be affected by where our vertex is. So our y value of this point hk, everything is going to be bigger than this. So if our parabola is facing upwards, our range is going to be greater than or equal to. So the y value here was k. Where if our parabola was facing downwards, the range in this case, this is really y is greater than or equal to k, is y is less than or equal to k. So we've been dealing with transformations. And so if we can get our function in this form of f of x is equal to a times x minus h quantity squared plus k, and then we can look at it and know what the vertex is and which direction our parabola is facing, depending on the value of the coefficient in front of the quantity squared. So the question is, how do we get it in this form? F of x equals a all times x minus h quantity squared plus k. So they told us in this formula that h is equal to negative b all over 2a, and k in this case is equal to 4ac minus b squared all over 4a. So I normally don't teach it this way, but basically what they're doing in here is completing the square. And so let's look at this case where it's a generic. We have a times x squared plus bx plus c. And we want to put it in this vertex form of a quadratic equation. So first thing that we need to do is we want this to be a perfect square. And so we know we can make things a perfect square by completing the square if that coefficient in front of the x squared is 1. So because this is a generic case, I don't know that that value of a is 1. And so let's factor a out of just the x terms. So I'm pulling a out of the x terms. So if I pull a out of a times x squared, I'm left with x squared. Plus, if I pull a out of b, that's like b divided by a. If I distribute the a there, I would get b times x. So technically here, I'm going to want to add something to make this a perfect square. Normally we added that number to both sides of our equation, but in this case, we're going to think of it as adding 0. So what we added, we're going to subtract off. And let's just first do that inside the parentheses. And then we have this plus c outside. So recall, in order to complete the square, we're looking for the number, same number that you would add to get b over a. We're taking that same number that we would add, which would be half of b over a. And then we're going to multiply it by itself. So we're going to square it. So let's just rewrite our complex fraction b over a divided by 2 over 1. That's a multiplication of the reciprocal. So flipping up, we get times 1 over 2 quantity squared. So we have b over 2a quantity squared. And then if I square my numerator, b squared all over 2a quantity squared is 4a squared. So I'm going to add this number, b squared all over 4a squared. And I'm going to subtract that number, b squared all over 4a squared. The thing is that the first 3 terms is our perfect square. We do not want this negative b squared all over 4a squared inside our parentheses. And so technically I can move that piece outside of my parentheses if I had distributed this negative or this a in there. And so if I did that, I have f of x is equal to a all times, let's rewrite this piece as a perfect square. So remember, it was that value before we squared it. So it's going to be x plus b over 2a quantity squared. And then we have minus the coefficient out front a times what we're pulling out, b squared all over 4a squared. And then we have this plus c. So let's just simplify this down a little bit. So I have A all times X. I'm going to rewrite it just in this form. This had a minus. So minus negative B over 2A, quantity squared. Notice this piece over here. I have an A in my numerator, cancels with one of them in the denominator. So I'm left with minus B squared over 4A. I want to add it to the C here, so I'm going to get a common denominator. I need to multiply the C by 4A over 4A. So this will be plus C times 4A all over 4A. So rewriting this, I have f of x is equal to A all times x minus a negative B over 2A, quantity squared. These are common denominators, so I can rewrite it as one fraction. And just so that it's in the same order that we have up here, I'm going to rewrite it as plus 4AC, just rewriting the order of my multiplication there, minus B squared all over 4A. So notice in this case, the H value is negative B over 2A. And my K value is 4AC minus B squared over 4A. So I don't have this memorized. This is something that our book had covered, and I was wanting to show where they got these values. But as long as we complete the square, we can get those values without having memorizing this H equals negative B over 2A, which I actually have memorized because of the vertex formula, which we'll talk about in a minute, but I don't have this K value because technically the vertex, if my X value is negative B over 2A, I can find my Y value by just plugging that value in wherever I see an X, because that's my X value, to get my Y value of the point. So another way to find the vertex is this way, using this formula. Now we're looking at an example to put everything together, what we've just talked about. So suppose that f of x is equal to x squared plus 2x minus 8. And we want to answer the following question. So put it in vertex form. And so let's start by doing that. And so looking at this, we have f of x is equal to x squared plus 2x. I'm going to want to complete the square on my x terms. And so let's leave some space here. So we're going to add some number in here. That's going to make this a perfect square, but whatever we add, we want to subtract. So it's like we're adding 0. And then we have a minus 8. And so the number that we would add to make this a perfect square. So half your B value, so half of 2 is 1. So 1 times 1 gives us 1. So we're going to add 1 and we're going to subtract 1. And so looking at this, I have f of x is equal to, this is a perfect square. The same number I add to get 2 and multiply to get 1 is 1. So this is x plus 1 quantity squared. And then we have minus 1 minus 8, so minus 9. So we have it in vertex form. Our vertex is HK. So it's opposite side in here. So I'm going to left one when there's a +1 added in there, and I'm going down 9 from my vertex. Originally on just x squared. So my vertex for my new function is -1, -9. So knowing where the vertex is and knowing if our parabola is facing up or down, we can tell if we're going to have an x-intercept or not. So looking at this and graphing this, or graphing what we have, I have a point at -1, -9. So when x is -1, my y value is -9. And my coefficient, my a value, well, there's nothing written there. So a is 1. This is bigger than 0. So I know my parabola faces upwards. And so knowing where the vertex is and knowing what way our parabola faces, we can tell if our graph is going to cross the x-axis or not. And knowing that I'm going upwards and my vertex is below the x-axis, I must cross the x-axis. Where if my value of a was less than 0, in this case, it's not, but if it was, I would be going downwards and I would see that my graph could not cross the x-axis there. So that could save me some time for looking for my x-intercept. If I plot my vertex or know what my vertex is, and if it's above or below the x-axis, and what direction my parabola is facing. So x-intercepts, we know that this is when our value of y is 0. So we're looking at when is x squared plus 2x minus 8 equals 0. Or we can look at our vertex form, x plus 1 quantity squared minus 9. When is that equal to 0? So sometimes when it's in the vertex form, it might be easier because we could just use our square root method that we've talked about before. Or if it's in standard form and not vertex form, see if you can factor it. So in this case, I see that either way is going to be fine. It's factorable, so we might as well just go through that way. There are two numbers that multiply to -8, but would add to a +2, and that would be +4 and -2. So we can factor that as x plus 4, all times the quantity x minus 2. Set each factor equal to 0. So I got x is -4, and I have x is 2. For my y-intercept, that is when our x value is 0. So if I look at plugging in 0 wherever I see an x in my original function, well, I get 0 squared plus 2 times 0. So those are still 0. And then I have -8. So this is equal to -8. So looking at this, we have our graph. Looks similar to this. It wants to find the axis of symmetry. So that's the vertical line that goes through our vertex. Just making it dotted because it's really not there. And so x equals -1 is that axis of symmetry. What is the point that is symmetrical to this point here that we're crossing the y-axis, which is 0, -8? Well, looking at this, which actually ends up being the same thing down here. Let's just talk about it because I just noticed that. Let's look at the distance. Because it's symmetrical across this line x equals 1, let's look at what the distance is from the axis of symmetry on the horizontal line to this point. So that distance here is 1, which means that distance on the other side also has to be 1. And so -1 subtract 1, my x value in this case is -2, my y value is -8. Finding the range. So remember, the range are all the y values that our graph is hitting. The smallest y value that my graph hits is my y value of my vertex, which is -9. So my range, y is greater than or equal to -9. Or we could put this in interval notation. So -9 with a bracket because we're including it, and then we're going to infinity. So we want to look at when it is our function f of x greater than 0. So we want to look at when is our graph above the x-axis. When is this function bigger than 0? When are we above this x-axis? So notice by just looking at the graph, we can do that. So we're above the x-axis for values of x which are less than -4. And we're above the x-axis here for x values which are bigger than 2. So we're above the x-axis from -infinity all the way to -4, but not including, union, everything from 2, not including, so parentheses, to comma infinity. So this last piece saying solve for f of x is equal to -8. Well, we would just take our equation x squared plus 2x minus 8 equals -8 if we needed to show it algebraically. So this is quadratic. We solve quadratics by sometimes setting it equal to 0. So let's add 8 to both sides to set it equal to 0. So we get x squared plus 2x is equal to 0. We could factor out an x. So this would be x times the quantity x plus 2 is equal to 0. So this is when x is 0, which we saw for the y-intercept. And x plus 2 is equal to 0 when x is equal to -2, which we talked about by looking at the axis of symmetry and the y-intercept and where that would have to be because it's symmetrical across that line x equals to -1. So I already stated how to find the vertex. We looked at that by when we were completing the square on the generic term of standard form of a quadratic, f of x equals ax squared plus bx plus c. I know that my x value is -b all over 2a. And I can find my y value by plugging that value in wherever I see an x in my original function, f of x. We talked about the axis of symmetry being that x value of our vertex. So x is equal to -b over 2a. We say the parabola is concave up if a is greater than 0. And our vertex would be a minimum point. And the graph we would say is concave down if a is less than 0. And our vertex would be a maximum point there. So concavity, we'll get more into when you get into calculus of finding where a function is concave up and concave down. But right now for parabolas, if a is greater than 0, it's concave up. If a is less than 0, it's concave down. And then x-intercepts. So we talked about where the vertex is. Knowing where the vertex is and the direction of the parabola will tell us if it's going to cross the x-axis or not. For instance, if we had a parabola that was facing upwards, but our vertex was in this first quadrant, there would be no x-intercept. Or an example where we have a parabola facing downwards and maybe our vertex is in the fourth quadrant, there would be no x-intercept. And so we could save some time by knowing where our vertex is and where it's the parabola is facing, or recall that we looked at the discriminant before. So the discriminant was part of the quadratic formula. This was the value where we could find what x is equal to. That set our quadratic equal to 0, which was negative b plus or minus the square root of b squared minus 4ac all over 2a. We talked about what was underneath the radical, this b squared minus 4ac. This is the discriminant. And this told us how many solutions we had and what type. It didn't tell us what the solution was, but it told us how many solutions and what type. If it had no x-intercepts, in this case, b squared minus 4ac, that would have given us a negative number underneath that radical. So that would have been less than 0. If this was bigger than 0, then we're going to cross the x-axis. And we're going to cross that x-axis in 2 spots. So this would have 2 distinct real solutions. So 2 x-intercepts. So we saw if it was less than 0, there was no x-intercept. And if it's equal to 0, well, negative b plus or minus 0 still gives me negative b. And so there is 1 x-intercept. And that's going to be that our vertex actually is going to be touching the x-axis somewhere. So here's cases where that b squared minus 4ac is equal to 0. So the discriminant can also help us to see if we're going to have any x-intercepts and what type our x-intercepts are going to be. So looking at an application of a quadratic functions. So the daily revenue R achieved by selling X boxes of candy is given by R of X. R of X is equal to 9.5x minus 0.04x squared. And this is the daily cost of selling X boxes of candy. Oh, actually, that was the revenue of selling X boxes. But if we want the cost of selling X boxes, the cost is 1.25x plus 250. So how many boxes of candy must the firm sell to maximize revenue? What is the maximum revenue? So we want to look at R of X, which is, again, let's rewrite it in this order, negative 0.04 x squared plus 9.5x. So I see that my A value in here is negative. And so if it's negative, that tells me that my parabola is facing downwards. And my maximum is going to occur here at this vertex. So I could complete the square here, which I really don't want to do, or I can use the formula that x is equal to negative b all over 2 times a. Well, in this case, our a was this negative 0.04, and our b value here is 9.5. So x is going to equal negative of b, which is 9.5, all over 2 times a, which was negative 0.04. So negative 9.5 divided by negative 0.08. Negative divided by negative is positive, and negative, or 9.5 divided by 0.08. So x is equal to 118.75 boxes of candy. Okay, but that, if we think about our question, it doesn't make sense to sell a portion of the candy. If I round it upwards, that's actually going to be giving me less. So we are actually going to round down. To the nearest integer. And so in order to maximize our revenue, we want to sell 118 boxes of candy. So we want to now look at what is that maximum revenue. And so looking at the maximum revenue, selling 118 boxes, we want to go in and we're going to look at our revenue function, and wherever we see an X, we're going to plug in 118. So we have 9.5 times 118 minus 0.04. See an X there, so plug in 118 quantity squared. So 9.5 times 118. This gives us 1,121 minus, so first square the 118 before you multiply it by the negative 0.04. So this would give me minus 556.96. So 1,121 minus that 556.96 gives us, oops, I subtracted a negative, right? But I should have just subtracted. 500, talking about money, our revenue would be $564.04 if we sold 118 boxes of candy. Technically, if we round it up, let's just see what happens. Let's just see if we had rounded up to 119. Let's make sure that our revenue isn't more there than it was for 118. So plugging that into the calculator, 9.5 times 119 minus, I'm going to square the 119, and I'm going to take that result and multiply it by 0.04. If you do this, actually, that's going to give us the maximum revenue, guys. If we do this, this is equal to $564.06. So technically 119 boxes gives us a little more, 2 cents more. So maybe seeing what this value is, look at what we're talking about. We're not going to sell a portion of our candy, of our box of candy to a customer. So look at the integers around that number and plug it in to see. So the next part says the profit is given by P of X is equal to our revenue, R of X, minus the cost, C of X. What is the profit function? So profit, just move over here a little bit. Is equal to revenue minus our cost. So our profit function is equal to the revenue function, which was 9.5x minus 0.04x squared, minus the cost function. So be careful here, that negative is going to be distributed to each term in our cost function. So we need parentheses around the whole cost function. So parentheses 1.25x plus 250. So I have 9.5x minus 0.04x squared. Distribute my negative. I have negative 1.25x minus 250. Combine like terms. I get my profit is negative 0.04x squared. 9.5x minus 9.5x minus 1.25x is equal to plus 8.25x minus 250. So that is part B. Part C, how many boxes of candy must the firm sell to maximize profit? What is the maximum profit? Okay, so again, we have a quadratic formula. I notice my A value, or we have a quadratic equation, and I notice my A value is negative, so it's parabola is facing down. I need to look at my vertex. And so I can find the vertex when x is negative b over 2a. So I'm looking at x is equal to negative b, so negative 8.25. All over 2 times a, which was negative 0.04. Make sure there's parentheses around the whole denominator if you plug the whole thing in so that it's thinking of it as order of operations. So in this case, x is equal to 103.125. So again, selling portion of a candy box doesn't make sense. So we're either going to round down to 103. We'll check them both. Or we're going to round up to 104. So that's a number. But what is the maximum profit? We would find that by plugging those values back into our profit function. So I want to look at what is P of 103. So negative 0.04 all times 103 squared plus 8.25 all times 103 minus 250. Okay, so plugging in 103, wherever I saw an X. So I have negative 0.04, parentheses 103, and parentheses just square that 103 plus 8.25 times 103 minus 250, which gives you approximately $175.39. Let me just look at the profit at 104. So just going back in and plugging in the same value, not the same value, but plugging in 104 wherever you see an X into that same equation. So if we do that, you should get 175. $175.36. So maximum profit is going to occur when we sell 103 boxes. And the profit that we're going to get back is $175.39. So provide an explanation to why the answers found in part A and C differ. Why is the quadratic function is a reasonable model for the revenue? Well, they differ because part A is asking for the maximum revenue, how much we need to sell to make the most money coming into the company. Where profit is how much revenue we're getting and then how much money that we are using to pay to make the product. So it's a difference between those two prices. So we just dealt with quadratic equations, functions. And so here's the summary of what we just talked about. You should be able to graph quadratic functions. F of x equals ax squared plus bx plus c. You got a couple different options on how to do that. You can put it in vertex form. F of x equals a, all times the quantity x minus h quantity squared plus k. And you could do that by completing the square. And then we can use transformations of functions to graph that. Or you can determine what the vertex is by finding the x value of the vertex, negative b over 2a. Plug that back in for x to get the y value of the vertex. We can graph the vertex. We can determine if our graph is going to cross the x-axis by the value of a and where the vertex is, or you can use the discriminant to see if there's any x-intercepts. Y-intercept, plug in 0 wherever you see an x. There will be one y-intercept. We can find any additional points using y-intercept and the axis of symmetry, and then we can plot and point our points and draw the graph.